So good afternoon, everybody. Welcome, and thank you very much for joining today's webinar organized by the European Nuclear Society. My name is Pau Aragon. I will be the moderator of this seminar, and I am a nuclear fuel researcher at the European Commission Joint Research Center in Karlsruhe, and also the chair of the Spanish Nuclear Society Young Generation Network. Today's topic, as you know, is advancing fuel design with sovereign solutions, in particular for VVER, and this stems from the response to the evolving VVER fuel market. Framatome is developing sovereign solutions for nuclear fuel designs, and this is supported by a comprehensive suite of fuel engineering services. These services are, as you will see, are based on codes and methodologies backed by decades of Framatome's experience. And today's session, the main goal is to provide an overview of some of these tools and approaches. You will see the technical maturity and readiness of these solutions for VVER applications in particular, including capabilities that extend to long-term dry storage as well. We have the pleasure to have as a speaker Dr. Bruno Miglierini, who has been working in the nuclear field for over 10 years with a primary focus on VVER type reactor and the nuclear fuel. He began his career at the Nuclear Research Institute Czech in the Czech Republic, then completed a 10-month IAEA appointment at the University of Illinois in 2016 and worked at the fuel cycle unit of a major European utility from 2017 to 2022. Since 2023, Dr. Miglierini has been working in the fuel business unit at Framatome, where he is responsible for the technological development and the management of VVER fuel engineering services for global clients. Now, moving to the structure of this seminar, it will last for an hour, in which you will have a presentation by Dr. Bruno Miglierini for around 30 minutes, and this will be followed by a question and answer session. I encourage you to, as Bruno is presenting, write your questions to the chat. And this way, hopefully, we will have a very fruitful discussion at the end of the presentation. So this is all from my side. And now, please, Bruno, the floor is yours. Thank you very much.
Thank you very much, Pau, for a very warm and friendly introduction. First of all, I maybe will share my screen to show you the presentation. This is quite important. So just a second. And okay. So Pau, if you can please just confirm that it is in a full screen mode.
Perfect.
Yes, okay. So good afternoon to all of you, colleagues, and I'm very happy that there is such a huge interest from all of you. As Pau already mentioned, I am involved and responsible for fuel engineering services, what means that I am responsible for implementation of our all VVER fuel products, whether we are talking about the VVER 1000 or VVER 440. And in this presentation, I will be more than happy to share some inside view how we at Framatome are working on development of fuel engineering for our products, and especially services. And as Pau already correctly mentioned, it is mainly about the codes, how we develop the codes, how we are preparing ourselves from methodology point of view, or for the application, for industrial application. So we will see this kind of brief overview because we do not have enough time to go through all of the topics in a more detailed way. However, what I would like to show you today is 4 points. First of all, I would like to introduce and explain how we as a fuel business unit at Framatome are at a glance, how we look like, what is our performance, what is our, let's say, size. And as you are well aware, I do not need to introduce our Framatome company too much. However, we are an international corporation based in France, but from a worldwide perspective, and with our perimeter, we are one of the biggest company in this sense. Afterwards, I would like to speak, of course, about the motivation, because as you know, there must be certain triggered point why to do the development, why to do such activities. So I will very briefly explain our Framatome fuel business unit motivation for the engineering services focused on a VVER fuel products. And the core part of my presentation will be focused on particular cases for the engineering services for determined domains, where I will explain you step by step which kind of procedures we already did, which kind of procedures we are planning to do, and what is our, let's say, basic overview of these engineering services. On the end, I would like to, of course, introduce some conclusion and takeaway message for you from this presentation. And what I would like to really emphasize today, I have a privilege to speak about this topic, but it's a teamwork of all of our colleagues, of our team members, of our experts, engineers, fellow experts, technical advisors. So it's only the top of the iceberg, what you will see today, but behind is really a huge effort of our engineers and experts. So first of all, as I mentioned to you, I would like to briefly introduce our fuel business unit, and of course, to give you certain introduction of our advanced products and solutions. So on this slide, you can see many nice pictures, but I would like to briefly comment only some of them. The first of all, I would say is really impressive. So we have more than 4,500 people in our fuel business unit. So you can imagine it's a huge amount of the experts, engineers, specialists around the world, because these people are based in 3 different countries. It's France, Germany, and United States. And also on your left-hand side, you can see the sketch of the map. In the United States, for instance, we have 2 locations, 2 sites. In France, we have the many and multiple facilities, factories, and research centers. In Germany, we have 3 special dedicated places for our fuel activities, especially Erlangen in Bavaria, then Karlstein in Bavaria, and the Lingen, which is the fabrication plant. What I would like to highlight it on this slide is the fact that whole our manufacturing supply chain is located in Europe, what means that we are absolutely independent from the manufacturing point of view when we are starting with the zirconium alloy until the fabrication of fuel assembly. So we have a whole supply chain based in Europe. So we do not need to rely on any other continents, sorry. And that's our really powerful tool. What I would like to also mention, we have a special 3 dedicated research centers. In fuel business unit, we are investing quite a lot of money into the research and development. It's a huge amount. We have special large programs for alloys development, special alloys. Then we have special programs for fuel development itself, for the design of the fuel, for the calculation codes, and other tools. So we have really huge program for different areas. So that's why we have dedicated research centers. And of course, we are the major player from delivery of the fuel on the market point of view. Just a few words. I already mentioned that we are mastering the entire process from the development of the fuel, from the design until manufacturing, and until to the contact with the customers, as a customer centers, sales, and of course with associated advanced calculation tools. When we are talking about the fuel types, we are focused on major reactor designs like pressurized water reactors, boiling water reactors, and of course VVER. That's a topic for our presentation today, and as well as for research reactors. Just a few words for the development of the design of fuel assemblies. We are starting from the very beginning of the designing of our products through the design, neutron characteristics of the fuel, thermohydraulic performance, thermo-mechanical performance, of course, mechanical capabilities of the fuel. And for all of these activities, we are using a special calculation codes. As I mentioned, we are starting from the production of zirconium and other necessary alloys for fabrication, then fabrication itself, until fabrication of fuel elements for research reactors. That's also domain what we are covering. And the target of this presentation today is focused on associated fuel services, especially for engineering. So engineering services means mainly calculations, methods, analysis. Then of course we have also field services activities, but this is focused on fuel assembly reparation or other activities related to the manipulation with the fuel. Today, as I mentioned, I would like to mainly speak about a few of our solutions. For instance, for the fuel codes and methods, as I mentioned, for the core design, for instance, safety analysis, core simulator, and of course for other fuel engineering and design activities. So this is what we everything do in the fuel business unit, and also fuel handling and conditioning, core monitoring. I will also speak today about the core monitoring system, Argos. So all of these activities we do in fuel business unit. So it's a large portfolio of activities. And then a few words about the motivation. As far as most of you are aware, Framatome has signed fuel contracts with the VVER fuel operators in Europe. And due to this fact, we of course feel obligation to assist and to help to our new customers and potentially future customers with the operation of VVER fuel. And that's the main motivation. Here on this slide, you can see the three main pillars of this approach. So we are mainly focusing on developing sovereign and independent fuel engineering services, what means that we are capable to work with these calculation codes or methods. And you will also see in the next couple of slides which kind of codes we have as a licensed codes, where we bought a license for them from the European companies, or the calculation codes which are in-house and we develop them by ourselves. And as I mentioned, it's really important for us to be support and to be helpful for our customers, for VVER operators, especially to provide with the engineering service and expertise. And what is the backbone for this? It's, as I mentioned several times until now, and that's about the deployment of various kind of European, respectively in-house calculation codes and methods based on our Framatome experience. Here, I would like to just start with this very simple overview, and later we go step by step through different kind of calculation codes for different domains. But what I would like to emphasize here is the fact that not only engineering service as calculations or analysis, but also field service tools are crucial for our work, because we are on the daily basis cooperating with our colleagues from a field service department, where they do some measurement or inspection of fuel assemblies. And thanks to this data, thanks to this measured database, we can validate our calculation codes, or even we can help with prediction of specific behavior of fuel assemblies in future operation. And that's a very nice synergy where you can see, or at least understand, that it's not only about the calculation part, but also about the measurement and real hardware work, where our field service colleagues are doing this kind of work and providing us with a support. As a nice example of this work is Colos system or software, where we do optimization of the core loading, and this is crucial. And I'm sure that some of you are working for utilities, that the operation time during the outage is one most crucial one, and the time savings is playing an important role every time because it costs money. So what we normally do for our customers for PWR, and we are working on this tool also for VVER customers, is optimization of the loading and unloading of the fuel assemblies thanks to this software Colos, where first of all our experts do prediction of the bow shape of fuel assemblies, and then we know and we can predict the behavior of fuel for the next couple of the cycles from the mechanical point of view, how the fuel will be behaving, how the shape will look like, and thanks to this we can optimize the manipulation and reshuffling with the fuel assemblies. So that's a Colos. And on your right hand side, I will come to this picture also later in this presentation. It's just a nice example of the whole model of a VVER 1000 core from the mechanical calculation code, where we afterwards, or our experts, are feeding this model with measure the data from the field experts, from the measurement of fuel, and making such a predictions. Yes, it's just an example for now. Then for advanced core design, here, as I mentioned already today, we are also using licensed codes for certain activities, like a Helios for nuclear fuel assembly design, or Andrea code, DIN3D core simulators. I will come to these codes later in my presentation, and you will see the calculation scheme and sequence, how we are working with these tools. Then our own tool, Athena code, it's actually for the neutron fluence analysis, where we do the calculation of the dose and the fluence of the neutrons on the reactor pressure vessel. And finally, on this list is just an example, Cobra FLX, the subchannel core thermohydraulic calculation code for safety purposes, safety analysis purposes. And of course, all of these codes can be utilized also for a safety analysis, especially for particular chapters in the safety analysis report, like a chapter 15, where you have initiated events, different initiated events for different scenarios, and these codes we are utilizing for such events. And here I'm coming to the core part of my presentation, and as I mentioned, I will only speak about certain examples, and the most important examples which I would like to share with you today is the work which we performed with the core simulation Andrea. Then I would like to introduce experimental benchmark, which we have started with our Czech partner for it's not only VVER specific experimental benchmark, but also for the real application, for industrial application, for our own work, and also for the community. I will come to this point, and I will be more than happy to speak about this project. Then a few words about the subchannel analysis with the Cobra FLX. Then, of course, as I mentioned already, core monitoring system, I would like to explain you how our modular system, core monitoring system, which has a modular features, consists, how it looks like, and how this tool is capable to perform the work for the monitoring of the core and the fuel. And of course, I would like to mention the fuel assembly bow prediction, as you have already seen on this nice picture before. So this is also part on my list today. So here, just for understanding of the perimeter where we are, let's say, located with all of our fuel products, and here specifically for VVER, is an environment where we have to take into account multiple effects. The first of all, of course, is the technology and physics, like reactor data, fuel assembly data, but of course a licensing environment in which we are located for a specific country, for a specific customer. So this is, of course, very important to understand, and based on this, to, if needed, adapt the scheme of the calculations, and of course then the licensing of our fuel products. But it's the same scheme or the same environment is applicable also for our engineering services, because this means that when we do the support for our customers, we have to be in the line with the local licensed requirements, with the, of course, requirements of the operator, and these multiple aspects are playing a crucial role. So this is our environment, this is our playground, where we have to taking into account all of the aspects. And when I speak about the codes, I already mentioned we have the license for the Helios code, where currently we do for our VVER fuel products the calculation for the lattice as a lattice code. For the purpose, you will see it later, we use Quadriga as an interface for the coupling with other core solver. It's mainly Andrea simulator, which we are also using and applying now. And for such a reason, when we do the simulations, we also use, for instance, for transient situations, DIN3D. So this is the neutronics package, which currently we are applying, and the scheme it's quite simple. So we have to use a Quadriga lattice code interface for extracted data from Helios to transfer this data to Andrea code, and for the application of DIN3D, we are working directly between Helios and DIN3D. So there is this data transfer of a cross-section libraries directly managed between these codes. Of course, when we are speaking about, let's say, reload safety evaluation, we have to have a certain tool. So we again use for this particular case CycleKit. So where we assess the safety or the key features of the core design to see whether we are fulfilling requirements. So that's a CycleKit for this purpose. For the thermo-mechanical analysis, we use Galilei, which is our Framatome tool, and it's quite obvious that for analysis with this thermo-mechanical code, we use, of course, the interaction with the neutronics codes, like a power histories, and of course we can, with the Galilei, calculate other fuel performance specific data from the thermomechanical point of view, which are needed for a neutronics calculations, like a fuel temperature of the tablets or other features which are needed for neutronics chain. Of course, then when I continue in this sequence, for the safety, for the safety analysis, we have to apply the system code. And for the system code, of course, we are also using extracted data from Galilei. And not only because, as I mentioned already, we have a subchannel called Cobra FLX, where we incorporate, or we can incorporate different kind of critical heat flux correlations based on the design of the fuel, of the specific VVER fuel, whether 1000 or 440. And for this subchannel analysis, we need forcing functions in order to do, let's say, the transient state for a subchannel analysis. And for such activities, we are extracting the forcing functions from a system code or from also neutronics calculation chain. So that's the basic overview of a communication channel between neutronics, thermomechanics, safety analysis, system code, and subchannel code. Just on a few examples, I will show you what we did in the former time for validation and verification. For instance, in the former time, we used the Temelin fresh core loading, where we simulated different kind of fuel assemblies with a different enrichment. And due to this fact, then we were studying how this fresh core for this validation and verification program is behaving, especially, for instance, here you can see rise to power for the different stages of the reactor core power, how we are, let's say, closing with our Andrea calculations of the relative power against the core monitoring data. So you can see it from the left to the right hand side, the scheme of the core, and of course the shape of the calculated results and comparison. And you can see the good agreement between Andrea results and the core monitoring results. So this is just an example what we did a few years ago for this kind of case. The same also exercise has been done for cycle depletion. So again, you can see the cycle burnup and boric acid concentration and how the curves are in the line. So of course we let's say compare the boron concentration, axial offset, and the overall conclusion from this verification and validation exercise is that there was a observed good agreement of the radial and axial power distribution during the power histories. Also, the axial offset in a good agreement with the measurement data during the cycle. So we concluded that it's a satisfied results, and that's the work which we did. For the neutronics part, also what I mentioned is experimental benchmark development. So we have initiated a project, we call it ENS, experimental validation of advanced neutronics codes for safety. And it's a Franco-Czech consortium where the Framatome is the leader on our side. And on the Czech side is the leader company UJV Řeš together with Research Center Řeš. So it's a French-Czech cooperation for the development of the experimental benchmark. And we have been funded by French National Research Agency and by Czech Technology Agency. And the project duration is for 3 years. So we started this year, recently, in February 2025. And the project will, will continue until end of 27. The total budget is approximately above 1.2 million of euros. And what is the main objective? So actually in this project, we have two main experimental parts. One, we call it experiment A. It's focused on investigation of the effect of fuel assembly bow on the neutronics calculations, and how we can do it on your right hand side. You can see simple scheme of the mini core, and this mini core we have assembled in LR0 research reactor in Czech Republic, and we do the different gaps between the fuel assemblies. We have the dedicated fuel rods which we measured after the experiment, and then we do the calculation part where we will simulate the same core condition or the same composition of the core, and we will based on this experimental data, measured data, compare our calculations. So it's a kind of benchmark which we would like to make publicly available. So it will be for all VVER operators and the research institutes available. But of course, when we were developing this project idea, we thought that we will focus not only on VVER type of reactors, but also for PWR. So these results can be applicable also for PWR type of reactors, at least as a validation database. So this is the experiment A. And for experiment B, we are planning to study the void effect, the void coefficient effect, where the certain dedicated fuel assembly in this mini core will be actually, or on this fuel assembly will be mounted special aluminum blocks, which will simulate the arrangement of the void effect. And then we do again a measurement and do the comparison with the calculation from our calculation tools. So this is this first part of this project. The second part, it's a long-term effort behind, because we already started with our Czech partner company UJV many years ago with other activities for VVER type of fuels and reactors. But since 2023, when we signed a memorandum of understanding, we initiated also multiple projects, including this ENS project. So the project is mainly focused on safety, reliability, economic efficiency of nuclear reactors, and to improve on the end, of course, the safety analysis or other analysis for the reactors. Yes, because thanks to this project, there will be many other, let's say, possible mitigation of the discrepancies and uncertainties for calculations finally. So that's a big contribution of this project. So just a few words, because time is running, for Cobra FLX optional analysis. On the right-hand side, you can see a nodalization of our calculation model in this suboptional code for a VVER 1000 fuel assembly. So Cobra, just for people who do not know this code, it's a global thermohydraulic analysis code, which is designed by our bureau. And what we did, of course, we did a verification and validation program with this code. And on this slide, you can see, for instance, comparison of the calculated mass flux with a different set of empirical two-phase flow correlations. For instance, for this particular case, we used a well-known correlation, which is available, just to make this comparison and show you the results. Then a few words about the core monitoring system Argos. I'm sure that many of you are aware about the core monitoring system. What is the primary purpose? Yes, is especially the collection of the plant data, to analyze them, to perform detailed physical calculation. That's the primary purpose, yes, to do the monitoring and collection of the data. And of course, then also prediction, yes, to predict the behavior of the core, of the fuel, of the safety key parameters of fuel, and to see how the core is in the real time corresponding with the prediction. And of course, implementation of key operator functionalities like automatic shutdown margin calculations, core tilt analysis, xenon prediction. But what I would like to say that for the Argos particularly, we have it as a modular system. So you can imagine it as a nutshell, which consists from different parts, which we can adapt based on the fuel, based on the power plant. So we can easily work on dedicated part of this versatile core monitoring system, whether we are talking about the graphical user interface or the prediction mode, or for instance the core simulator, which can be of course used based on our customers' request. Yes, so it's the modular versatile system, which is quite flexible, and we work on it. Few words about fuel assembly bow prediction. On left-hand side, you can see some nice pictures as an example. And I mentioned this at least 3 times today, but it's very complex activity. It's not only mechanical part, but in our models, it's much complex topic. So we of course include fluid dynamics. We are taking into account the thermohydraulics. So it's a very complex activity. On this slide, for instance, you can see just from the mechanical analysis, or for the part of the mechanical analysis, you can see some nice pictures. These are, for instance, dedicated for VVER 1000. And what I would like to say that first of all, we do this kind of prediction with the expert code, which we have developed in Framatome. And afterwards, we are, of course, communicating with the Colos system for this prediction. So on the one hand side, we can do the prediction of the fuel assembly ball. And on the other side, we can optimize the manipulation with it. And what is also good to mention, that we validate these models from the real measured data. And that's a point what I also mentioned today. We work quite closely with our field fuel experts who are performing the measurement of the fuel bowl or other parameters like a twist or elongation. Also a few words on the end, because we mentioned it on the very beginning today, also by our moderator Pau, for the long-term storage. This is crucial issue for a VVER region, definitely, because the deep geological repository or other type of repositories are under construction or are in certain countries, but in certain countries still under designing or location or appropriate location definition. And due to this fact, not only for VVER customers, but also for our other customers, we do the long-term storage analysis, especially prediction of the behavior of fuel cladding. And here you can see very simple scheme how this sequence is working. So from the left-hand side, it's the end-of-life fuel properties, which we are calculating from the fuel rod performance code, and also the data from the cask supplier or other, let's say, operator of the storage facility where you have the spent nuclear fuel casks. And then we need, of course, the temperature profile of the cask and other parameters, how the cask itself is behaving. And these two parts, the blue one and the orange one, are entering into our CSAS code for the cladding strain and stress calculations, where we can analyze and predict cladding strain and stress from a long-term storage point of view. So this is tool where we are working on this thermo-mechanical, let's say, part of analysis, and to investigate how the fuel rod cladding, not only, but especially fuel rod cladding is behaving. Just a conclusion, because we are running out of the time. So as on the very beginning, I mentioned these main pillars for our motivation and for the let's say development activities for engineering services and for the support of our customers. The main message for you as a takeaway, it's we are continuously expanding these services. Yes, it's not easy just to do it from day to day. Yes, it must be a certain long-term effort behind. But we are working and we are committed, of course, working on it, not only for engineering, but also for field services activities. And finally, of course, we are committed not only to help to our existing customers, but also future customers to improve effective and flexible operation of the fuel. That's, of course, the main point by a power plant operator. We understand this, of course. So it's to optimize the uranium utilization and prolongation of the fuel cycles, higher burn-up, higher enrichment. All of these topics are on the table today. For sure, we are working on this as well. And today you have seen only a few examples, and that's what I would like to say again, because it's the top of the iceberg, and it's not easy in 30 minutes to explain all of the topics. However, we are very glad that we can share this with this international community on this platform on ENS webinar. And I'm very glad that you were attending, and thank you very much for your time. And please feel free to ask questions, and thank you for your attention.
Thank you very much, Bruno, for this very interesting presentation. And the questions indeed confirm that it was very interesting. I will read them from the chat. I will also try to group the ones that are related to the same topic. And let's start with SMRs. Can you say something about the fuel for water-cooled SMRs? And also related to that, did you make tests for SMR fuel? Have you been contacted for new designers for SMR reactors?
This is interesting question. Thank you for that. SMR, it's very interesting topic nowadays. And yes, Framatome, we are working on the SMR fuel, and we are in a contact with the designers of SMR. Yes.
Okay, thank you. Then about the enrichment range. So what is the range of enrichment and the absorbing dopant concentration in this experimental benchmark that you presented in your slides?
Well, I do not have it from the top of my head. However, we decided for a quite low enrichment. But if you are interested in more details, our colleague will present the configuration of this benchmark next year in 2026 on a Pfizer conference. But if you are asking about the range, if I remember correctly, it was quite small. I think between 2 and 3% of the enrichment. But you will see more the details on the conference next year.
Okay. So now it's a double question. Two independent questions from the same people and the same person. Will you consider the Russian material E110 and other specifications for your study, or the materials are based on your own productions? Maybe we can address this first and then we move to the other.
Well, here I would maybe also split this question on two parts, because one part is when you do the code development and you are working with, let's say, the first validation of your calculation codes, then you can work with publicly available data. Yes, that's my response regarding to, for instance, code development. But when you when you do the real calculations, for instance, for our own design, for other, let's say, designs of our fuel fleet, then we are working with our own materials. So actually, it's yes and no, but as I said, based on the specific case, for which purpose you want to do the calculations.
Okay. We will move to another one. They are also asking about the reprocessing. Are there any engineering services from Framatome devoted to this stage of the fuel cycle?
For reprocessing activities, well, I would say that in the fuel business unit, what we normally do is, of course, the calculation for the spent fuel itself. So if we are talking about the decay heat or the neutronics characteristics of fuel, or let's say other performance when the fuel is already stored or prepared for dispatch for reprocessing. So this is what we normally do. And in our business units in Framatome, because we are a large company, we have more than 21,000 employees right now. So we have also business unit focused on the IB or installed base activities or special activities for other, let's say, power plants. And we normally also do certain service or support for the backend activities. So I would say yes. As a Framatome, we do activities for the backend regarding to calculations, but the question is which particular you mean. And as a fuel business unit, we also are interested in, and we normally do the decay heat calculations or spent fuel calculations. So yes.
Okay. Now, related to licensing, what is the expected timeline for the fuel licensing of the Framatome solution for VVER fuel? And also, do you anticipate any in reactor testing to be a bottleneck in the process?
Well, this is also good question, and what I can say again, I can respond on the two ways. One is that due to the political situation, we were, let's say, faced with the fact that our customers wanted to have incumbent fuel or the traditional fuel like this, and this is something what we are using as a short-term solution for our customers. And that's regarding to licensing, it's not the subject of the licensing because this fuel it's already, let's say, well known in the VVER community. When I'm talking about the own design fuel, this is something where, of course, are multiple negotiations on the different levels. And where we can expect this, I would suggest to look also on our conference material. I think we presented something in the NESA bar a few weeks ago. So we are expecting to, let's say, be ready with the fuel products and with the licensing in the next couple of years. So it's behind the door, I would say.
This actually, I think it addresses partially the next question, which is about, they were asking about a few words on the own design of VVER fuel from Framatome. So this is what we can expect in a timeline of 2 years from now, something like that. Or do you want to add something else to that?
I don't see now the time schedule in front of me, but if somebody is interested in, we have presented the materials, and I think it's a couple of years ahead of now. So yes.
Okay. So here comes a long question. What are the most effective strategies to build robust confidence and credibility in in-house computational models, especially for new fuel times and in regions lacking experimental data?
Well, this is quite long.
It's even longer, but I think we can stop the question here.
Can you maybe repeat it?
Yeah. So how do we build confidence and trust in the predictions of our in-house codes, especially for new fuel types or for fuel types that have not previously been used in a specific region?
Okay, I understand. Well, yes, this is good question because I think the author is focusing maybe on the fact how we are using our competencies and experience from PWR or boiling water reactors and adapting these codes or methods for VVER or other new let's say fuel products or new reactors. Well, of course, what I can say, first of all, you have to have a calculation code which has been validated in a former time. If, for instance, if it's a PWR, and then you have to have also methodology. It's not only the calculation code, because this is just like a calculator with a specific thermomechanics or thermo-mechanical or neutronics equations. So, but you have to have also the methodological approach, and the methodological approach is quite versatile generally, because of course you can have a different, let's say, fuel limits, criterias, that's for sure. You can have also different requirements from the operator because of a different, I don't know, the operation sequence or different boron concentration for sure. But the basic stone for all of your activities, you need a versatile methodology, which it's based mainly on the experience. When we are talking about a VVER, it's a quite similar. So we also started with our, let's say, methodological approaches, which we developed decades and decades ago, and we continuously improve them. So we are not starting from the scratch. So you have to have certain proven track history as a fuel vendor to show that you can be confident. And then, of course, when you are asking about the confidence of the, for instance, results, normally what, of course, we do are the international benchmarks to do validation and verification programs. Or you can have the real measured data directly from the power plant, if possible. And that's the traditional way how to do validation and verification of the calculation codes. So that's one. And have I missed something from this question, or that's all?
I think that the answer is quite comprehensive. I think it addresses the topic. I would say it's enough. Yes. Okay. The next one is actually not about VVR, but okay, we can give it a try. Can you say something about future plans of Framatome about fast reactors in terms of fuel designs?
Well, to be honest, I'm not an expert in fast reactors, nor the manager for it, so I'm sorry.
I
really
understand.
don't know.
It's okay. So if we can focus the questions on the topic of the seminar, apologies, then that would be better. So now comes a question that is also related to another one below about ATF or advanced technology fuels. Okay, so if you're familiar with the CERMET design, so UO2 particles dispersed in metal, do you think that that could be applied to VVR? And also a more generic question: is Framatome exploring any ATF concepts tailored for VVR?
Well, this is interesting. Okay, I mean, regarding to the cladding materials, this is one huge domain. Yes, it's a one huge domain. And of course, we have our own materials for the cladding and for different components. And for instance, ATF materials, we have just an example, ATF program. And we started with this in the United States a couple of years ago, and we went through the irradiation program in the real reactor, not only with the fuel rods or pins, but with the whole fuel assembly. So with all the bundles were irradiated. So we have the huge program just for EATF. But regarding to the application for VVR, it's based on the customers. Yes, it's based on the customer's preference, but we generally are, let's say, ready to provide such a requested type of alloys if needed. So yes, we work on it, and yes, we are ready to deploy if needed.
Thank you. Next is the very specific question on the fuel assembly bow inspection or measurement. What is the scope for cycle bow predictions? How will it fit outage schedule?
Well, this is very challenging. That's true. This is very challenging. Again, based on the type of reactor, yes, because for instance, for PWR, there is a measurement which is performed for each fuel assembly in the core, and it's according to the schedule of the outage. In a VVR, it can be much more challenging because of the design of the VVR 1000, particularly because the bow effect is more relevant for VVR 1000. So for this one, of course, we have had already investigated how to do the quick, let's say, measurement and to validate such a prediction models, because it's not easy. So yes, we know that, for instance, in VVR 1000, this is a specifically big challenge because there is no need to measure all fuel assemblies of the core. However, we elaborated the scheme how we can proceed and not to impact the outage, because as you know, during the outage, each second it's counting and each second costs money. So yes, we are aware about this, and we have developed scheme and sequence for VVR 1000 reactor core.
Then, if that's okay, we will have two last questions. The first one is: do you use any code to calculate the control rod in your studies?
Yes, I mean, we are taking into account control rods, that's for sure. So yeah, yes.
Okay. I guess it's in the neutronics code that you introduced. Okay. And then the last one, for the mechanical vibration analysis, could you use VTran code for VVR fuel as well, or the code needs to be validated for this design first?
Well, for the I will say that for the mechanical analysis, generally we use our own calculation codes. It's KW-USTOS, for instance, or other licensed codes from our portfolio. And for the designing of the fuel assemblies, and for the vibration analysis or some other, let's say, let's call it transient situations, we also do this calculation with the mechanical codes, but especially with our in-house or licensed. So that's what I can say.
Okay. Then, yeah, I think we can conclude here the questions. Thank you so much, Bruno, for answering all of them. Also very comprehensive answers. So thanks for the time and effort. And finally, so I would like to conclude this seminar on behalf of the European Nuclear Society. And thank you, all of you, all the attendants, for devoting some of your lunchtime to this interesting seminar. I hope it was enriching and that the discussion on the questions and the presentation from Bruno was useful to your fields. And then, of course, thank you very much to our speaker, Dr. Bruno Miglierini, for agreeing to be a speaker on this seminar and for doing such a great job with the presentation. Thank you very much and have a good day.
Thank you very much to all of you. Bye bye.